In this video, I'm going to discuss Green's theorem. So Green's theorem gives a relationship between a line integral around a simple closed curve C and a double integral over the plane region D, which is bounded by C. All right, so we see figure 1. Assume that D consists of all points inside C as well as all points on C. All right. In stating Green's theorem, we use the convention that the positive orientation of a simple closed curve C refers to a single counterclockwise traversal of C. Thus, if C is given by the vector function r of t, where t spans from A to B, then the region D is always on the left side as the point r of t traverses C. So you'll see here in figure 2a, it's traversing around D counterclockwise. And it's closing D. So D includes what's inside the closed curve and also the closed curve itself. A negative orientation basically would give you a negative value, and that's going clockwise. So here we are. This is Green's theorem. Let C be a positively oriented piecewise smooth curve. Right? Simple and closed. So some sort of simple and closed curve. Positively oriented. So that's counterclockwise. And that's C. In the plane, right? In the plane, XY. And let D be the region bounded by C, so that's D. If P and Q have continuous partial derivatives on an open region that contains D, then we have this relationship between a line integral and the double integral. And you'll notice something familiar here with the fundamental theorem of calculus, right? So you've got derivatives on one side, derivative q with respect to x, and then derivative p with respect to y. And you see this analogous, right? Okay. So p and q being those scalar functions that are in front of I and j. All right. So we're going to do an example here. What we're going to do is, so let's just back up 1 second. So I want you to note that you can go in reverse, right? So if it's difficult to find the double derivative, then you would calculate the line integral, right? So if the line integral is tough, then it might be prudent of you to use the double integral. All right, so we're going to evaluate the integral, the line integral of x to the fourth around the closed, where C is the triangular curve consisting of line segments from 0, 0, 1, 0, from 1, 0 to 0, 1, and from 0, 1 to 0, 0, right? So I think we'll have, I want to see that graph here. There we go. So we have a graph there. So you'll see that this is what we're talking about. Again, we can apply Green's theorem because this is a closed, piecewise smooth closed curve, right? And also because we also have a counterclockwise orientation in which we're talking about D being the area inside of C and C itself. So I'm just going to read this for you. Although the given line integral could be evaluated as usual by the usual methods, by doing the line integral, that would involve setting up 3 separate integrals, right, along 3 sides of the triangle. So let's use Green's theorem instead. Notice that the region D enclosed by C is simple, and C has a positive orientation, which I just mentioned. So that's what we're talking about. We're talking about this region. Just noting that this line here is y equals 1 minus x. Okay, so we see here we've got p being the x to the fourth and q being xy. So here we go, as stated. Then we have this line integral equaling this double integral, and we're going to need to take the derivative with respect to x, dq dx, and dp dy with respect to y. We went ahead and did that. Oops. All right. Oh, let's go back to that. Sorry. All right. So we went ahead and did that. We know we're going from y is going from 0 to the 1 minus x, and x is going from 0 to 1. So this is a pretty simple double integral, iterated integral here, right? So we're evaluating the inner integral, and we go ahead and did that from 0 to 1 minus x, and then we can evaluate this outer integral, and we end up with 1/6. So it becomes much easier to do this double integral than the line integral. Now, you could go back the other way, right? So it really depends on the question at hand. If you're given a double integral, just note that if it's a closed curve around that d, you can go ahead and do the line integral.